Alright, welcome to another AQA AS chemistry video. We've now finished the physical side of, or at least the AS physical and AS organic chemistry now. And now we're going to go into AS inorganic chemistry. It won't take long. It's quite a quick topic and fast. There's not a lot on it. In fact, I've already finished the first two videos of this topic already. And it's kind of going to, it covers, well, I'm going to do the periodic table today, and it's kind of covering some of the themes are in year one, or so in physical year one. Even in year two, it kind of covers what some of the things are in physical chemistry, but it just goes in a little bit more depth. Yeah, I'm gonna go straight into it. So, kind of cancel that out. Right, the periodic table. So groups and periods. The periodic table is arranged into groups and periods, as we already know from physical chemistry. The periodic table is a table that organizes all the elements into groups and periods. The elements are arranged in order of proton number, starting with hydrogen. That is the proton number of 1. So basically, in case you didn't, I always, when I first did chemistry, I didn't really think about it like that. I don't know why, but it's just as you go, the periodic table is just arranged in proton number, or the atomic number, right? And it's just 1, 2, 3, 4, 5, 6, 7, 8, and that's how they're arranged. Obviously, the MR, the AR, the relative atomic mass can be a bit different, but overall, the periodic table is just arranged in atomic number from 1 to, well, how many are there? 116. Yeah, there you go. But yeah, that's something that probably everyone already knew. A period is a row on the periodic table. Elements in the same period have the valence electrons in the same shell. The diagram highlights period 3. So periods are just the rows. The valence electrons, or the outermost electron, right? The outermost electron is on the same energy level when it's on the same period, right? And if we're talking about period 3, it means that the outermost electrons are all on the third energy level. So it's 3 energy levels, and the outermost electrons on that third energy level. So if you look at sodium 281, 282, 3, 4, 5, 6, 7, 8, and they're all on the same energy level. Don't think about them as the 288 rule, because I said before in chemistry we don't do that. We do the 1s2, 2s2. We have the orbitals, right? But yeah, when we're talking about periods, they're just on the same. The valence electron, or the outermost electron, is on the same energy level. And here we got period 3 examples. In fact, in general, when we go through the examples in the exams, they like using period 3 a lot. So just kind of get familiar with it. I think it is in year 1 chemistry. I think it is year 1 inorganic chemistry, where they go into detail about the ionization energies, and I'll go through it when it comes up. But there's slight variations when you're talking about ionization energies. Size is relatively constant, but we'll go through that, all right? So period examples: the magnesium and sulfur are in the same period. In simple terms, they have the same electronic configuration as I said before. So same magnesium, sulfur, same period. So the valence electrons are all on the same energy level. They're both on the third energy level, or same shell energy level, whichever tickles your fancy. Groups. So a group is a column in the periodic table. Elements in the same group have their electrons in similar orbitals. They often have very similar properties. A group N element has N valence electrons. So groups in group 4 have 4 valence electrons. So in this diagram highlights group 7. So they have the same as you go down the group, there's the same N valence electrons on its outermost shell, but it just increases by 1. So say you had 1 electron on your outermost shell, like in period 1, right? So in group 1, you still have 1 electron on its outermost shell, but it just increases in shell size. So it'll be, in this one, there's 2 energy levels, and on the second energy level, because it's group 2, right? There's just another. It's just the outermost electron has more shells. Group 3 has sorry, I'm rephrasing this wrongly. Group 1, right? That's helium. Group 1, hydrogen, 1 electron in its outermost shell. Group 2, so group when you're talking about so I keep talking about periods. I need to rephrase my wording here, sorry. If we're talking about period 1, right, hydrogen's has one energy level, right, and there's one electron in its outermost shell, because there's only one shell. As you go down the same group, but we don't group 1, but period 2, lithium has one electron in its outermost shell, but it has two shells. Period 3, but still in group 1, you kind of see the theme here, right? There's going to be there's three outer shells, there's three shells, and the outermost shell has one electron. Four shells, outermost shell has one electron, so on and so on and so on as you go down the group. But the common theme is that the outermost electron has has the same number of valence electrons, but the number of shells will just increase by one. And it's the same thing here. There's 7 electrons on the outermost shell, but the shell size so it will just increase, and that's what's happening. But you should know that by now, by GCC. I think people understood what I was trying to say. I may have messed up a bit, but I think people generally understand what I'm trying to say here. The outermost electron has the same number of electrons. There's the same number of electrons in the outermost shell, but number of shells will just increase by 1 as you go down the group, I mean. So, for example, the halogens are all in group 7, but fluorine simplified electron configuration is 2,7. Chlorine, which is 1 down, because fluorine is in group is in period 2. Chlorine, which is in period 3, has 1 extra shell, but it still has the same number of electrons on its outermost shell. And if we went down again to bromine, it would be, I don't know what would be the electron configuration, but it would be it will still have 7 electrons on its outermost shell, but it will just have an extra electron on that shell. Sorry, it will have 7 electrons on its outermost shell, but it will just be another energy level. There we go. I have to make sure that my wording isn't complicated here, so I don't confuse anyone. If it was bromine, 2, 8, whatever the next one is, but then the last energy level you know is going to be 7. We see they both have the same number of valence electrons here. So we also know that halogens are very similar in the chemical properties. So because they have the same number of electrons in its outermost shell, that in turn causes them to have very similar chemical properties. The outermost shell, which is usually called the valence shell, holds the valence electrons. Valence electrons are the electrons that would react. That's why they're assigned as valence electrons. Lone pairs are different to bonding pairs of electrons, but valence electrons are the electrons that are involved in the reaction, at least, or involved when bonds are formed. I said bond forming and bond breaking are what are essentially what reactions are. Essentially, if you think about it. So if they all have the same number of electron shells, they would if they all have the same number of valence electrons on the outermost shell, they ideally have the same properties. Whereas with periods, they don't have that. The electrons are on the same energy level, but the electrons are on the same energy level, but it's different number of valence electrons on that same energy level. So they have different chemical properties. So periods have different properties, but groups would all have the same properties. The rate of reaction on that period would be different, but ideally the type of reaction would you expect to be generally the same. For example, if you're talking about, if everyone knows from GCC, when you drop magnesium in water, also if you drop group 1 metals in water, they generally have the same properties. They'll generally have the same form the same products. Magnesium into water, magnesium hydroxide, hydrogen gas. But you know that so I shouldn't use magnesium. Let's say lithium, right? Lithium in water, lithium hydroxide, and hydrogen gas. But as you go down the group, and some of them are they're so unreacted that the properties might be slightly different. That's they're not 100% the same, but generally the same. But you know that a sodium is the same type of reaction, but it's just faster. Potassium goes on it, and as you go down the group, because you have more shells, as you go down the group, as I said before, because you have more shells, more shielding, that there's a weaker electrostatic attraction. The nuclear charge may increase, but because the shell size is also increased and there's more electron shielding, there's a weaker electrostatic attraction between the nucleus and outermost electron, and that makes it easier for, if you're talking about the metal reacting with water. So you can see francium would have a very explosive reaction with water because it so easily loses an electron and so easily does a reaction with water, and very quickly and rapidly does a reaction with water. So yeah, just knowing the differences between groups and periods, you should know this from GCSE. I probably went a bit too overboard there, but yeah. But anyway, now I'm gonna go to differences. That's GCSE understanding, and I'm gonna go into differences into when you're talking about A level understanding. And as you should know what SP and D and F blocks are, but I make it here. So the two leftmost columns make up. So the periodic table can be organized into 4 sections. These are labeled as S, P, D, and F blocks. And when we talked about the different orbitals, S, P, D, and F. So I'm going to go into here. I think I should have gone through this topic in physical chemistry. Yeah, I should have gone through this topic in physical chemistry. But here, this is where you can clearly see the trend with S, P, D, and F orbitals, because they can be arranged in blocks. So the S block, right? So the two leftmost columns make up the S block, and this is called the S block. So, and we oh, did I make a mistake there? Yeah. The two leftmost columns, I should include technically hydrogen is probably in this as well actually. Ooh. Yeah. There we go. So this is called the S block because elements in it have all their valence electrons in its S orbital. So note also helium is also an S block element because it has the electrons configuration of 1s2. So any element that has its valence electrons, which means its outermost electrons, the electrons that react in the S block, they're considered S block elements. And all of the metals, all the alkali earth metals, I should say all the alkali metals and alkali earth metals, hydrogen and helium included, all have their valence electrons on in the S block or in the S orbital, I should say. And therefore, it's important to categorize them like this because it makes it easier to say, because these elements all have very similar properties, and technically hydrogen and helium could have similar properties to metals, and you can clearly see why, because of those electrons. You can see obviously not the same as metals, but they have some certain reactions, they kind of have similar properties, and that's because they are their electrons are within the S orbital. I'm going to move on now. So the P block. The 6 rightmost columns make up the P block. And this is called the P block because the elements in the P block have a partially filled P subshell. So, as I said before, same principle with the S block, but that their valence electrons are on the P orbital. And as they all have, these are all the gases, right? I think yeah, these are all the gases here, apart from helium and hydrogen, of course. But you can clearly see they all kind of have similar properties. So apart from, obviously, aluminium is part of this group. Aluminium's got a part of this group, but it has it helps out knowing which groups everything is. There is a reason for it because aluminium, although it's a metal, it's kind of considered more of a metalloid because it has certain properties that you wouldn't expect from a casual metal or the generally regarded metals such as the alkali earth metals, the alkali metals, the alkali earth metals, the transition metals. It's a P block. It's in the P block, and as I said before, the valence electrons determine the reaction, and aluminium has properties that are that you wouldn't really expect from no metal. They're not generally magnetic. They have a very high melting point, one of the highest actually, but generally very thin, brittle. But they have properties that are different, and and this is the reason why. We always kind of in chemistry kind of say it's an element in this. It's generally this regarded as this, but it doesn't have the properties of this, and that's why it's a metal, but it doesn't always have the properties of the usual metals, and that's the reason why it's a P block element. The D block lies between the S and the P blocks. Elements in the D blocks have a partially filled D subshell. Sorry, I said, you can see a pattern here, right? If its valence electrons are in the D subshell, the P subshell, the S subshell, but if you're talking about the D subshell here, it's because they fall into that block. So if it has valence electrons on the D subshell, it's in the D block. And the D block lies between the S and the P blocks. So one thing that people generally in GCSE, you're generally taught that elements in this group here are called transition metals. When you come to A level, you'll come to understand that that isn't the case. Generally most of them are, but only elements in the D block that form a stable ions with a partially filled D subshell are called transition metals. If they don't, they're not considered as transition metals and are simply regarded as D block elements, like scandium, and I believe zinc as well. There's some, so only if this, I believe this is more of a year 2 thing, but in case it is year 1, no, I think it's year 2. I think it's year 2, but only elements. Oh, don't want that. You know what? Actually, it's good. Only elements in the D block that form stable ions for partially filled D subshell are called transition metals. Yes. The reasons for that you're coming to more into year 2. I'm not gonna go into that because I don't want to confuse people. People are probably looking at that and saying, "What the hell's going on?" I don't really fully get that, but it's just to get into your head that when you're talking about the D subshells, have I gone properly into D subshells? I think I surely have gone through, but anyway, yeah, I think I have gone through. So, but you know, this is the D shell here. Should have been what, 5? 1, 2, 3, and 4 and 5. And I already explained to you that you have to be filling them equally like this. I think I definitely should have gone through it. Right. So the reason why it has to have the reason why transition metals need to have a partially filled D subshell is more to do with the fact of what are the properties of a transition metal that you can remember from GCSE, right? Obviously from GCSE you know they're strong, brittle, but you also know that they can form colored ions, and they're useful as catalysts. You have to, as I said before, I'm trying not to go through too much of it in detail, but in order to get some of those properties, and for example, a catalyst, it needs to have a partially filled D subshell, and to be regarded as a to be a good catalyst, or even just to be regarded as a transition metal, to have some of these properties, right? But zinc, scandium, they don't have these properties, so they can't be regarded as transition metals. They're just regarded as D block. Let's just say D block. They should just be regarded as just D block elements. All right. Let's go for it now. The F block. You don't need to know too much about the F block because you don't study it in A level chemistry, but just to know that the F block is attached along the bottom of the periodic table. These are usually your radioactive compounds, very large nucleus compounds, heavy nucleus compounds, is something that they're called. Elements in the F block have partially filled F subshells. These elements are referred to as lanthanides and actinides, the top and bottom row respectively. So so the top rows are called lanthanides and bottom rows called actinides. You don't need to know about this in A level chemistry because maybe in physics, I didn't study physics, but yeah, this F flux never come up, so don't have to worry about that. Yeah, but that's the end of this video. Hopefully it was helpful.